Okay, so we're here for the last part of this lesson. And before we start writing the important ideas here, we're going to do a little review from chapter 7. We're going to do a summary. And what chapter 7 did was we were looking at the sampling distribution. And we looked at sample proportions and sample means. Now today we're going to do sample proportions. So the sampling distribution of sample proportions and we can talk about the shape, the center, and the spread. The shape of a sampling distribution of a sample proportion is going to be approximately normal. As long as the sample size times the proportion is greater than or equal to 10, and then the sample size n times 1 minus p is also greater than or equal to 10. Okay, so this is what we call the large counts condition. If n times p and n times 1 minus p, this is the number of successes and this is the number of failures. So the number of times that something does happen that we're looking at and the number of times that it doesn't happen, as long as both of those are greater than or equal to 10, we can use a normal approximation to find the probability of something happening for that. Okay, so that will be the shape. This is going back to chapter 7, if we're dealing with one proportion. So we have shape, we have the spread, and we have the center. Let me put the center next. The center of a sampling distribution, remember that the mean of all the possible samples of size n, if we took every possible sample that we could get, the mean of those samples is going to be equal, of those sample proportions, is equal to the true proportion. If we take random samples, if we take samples, we'll get some that are less than the true proportion, some that are greater than. But if we take every possible sample proportion that we can of size n, and we take the mean of all of those, we will get the true proportion. Okay, so that was the center. And then the last part, we talked about the spread of the sampling distribution of a sample proportion. And that, the standard deviation is talking about the spread, and we had a formula for that. It was the square root of p times 1 minus p divided by n, which is the sample size. Now that is assuming, that's assuming as long as our sample size is less than or equal to 1/10 of the total population size. Right, that's the 10% rule for independence. Okay, now that's what we learned in chapter 7. That was for one proportion. So what we're doing in chapter 10 here, in section 1, is we're going to say, well, what happens if we have two proportions? What if we take a difference of proportions? All right, so when we have a sampling distribution, of a difference of sample proportions, okay, I'll say diff sample proportions, so which is p hat 1 minus p hat 2, the first sample proportion minus the second sample proportion for that. The shape is approximately normal, just like what we found in chapter 7, as long as the large counts condition fits. Now the thing is, since we are comparing, we're not just looking at one proportion now, we're looking at two different proportions. So what we have to do is take the first sample size times the first proportion, and the first sample size times 1 minus the first proportion, both of those must be greater than or equal to 10. Okay, so that's for the first proportion. But then the same thing has to be true for the second proportion. We have to take the second sample size times the proportion, and then the second sample size times 1 minus that. Those both have to be greater than or equal to 10. So we've got to check the large counts for each of our proportions here. But as long as all of that is greater than or equal to 10, we can approximate this with a normal distribution. That's the shape. When we take the center, when we look at the center of a sampling distribution of sample proportions, so the mean of p hat 1 minus p hat 2, the sampling mean of the difference of sample proportions will be equal to the difference of the true proportions. Okay, so it's the same thing that we had up here, that this will equal to the true proportion in the long run if we look at all the possible samples. If we look at all the possible distribution of sample proportions, then we will get the same as P1 minus P2. So we have the shape, we have the center. Now the last one is the spread. So we're looking at the standard deviation. The standard deviation of the difference of sample proportions. So p hat 1 minus p hat 2. Now this is going to look confusing. It'll be p sub 1, so the first proportion, times 1 minus the first proportion divided by the sample size of the first proportion, plus p sub 2 times 1 minus p sub 2 divided by the second sample size. All right, so basically we're doing a difference of proportions, so we're going to do this twice. And one other thing that we learned, if you think back to when we did the sum and difference of standard deviations, for example, if we did the standard deviation of x plus y, that was the square root of the standard deviation of x squared plus the standard deviation of y squared. And that's actually the same thing for the standard deviation of x minus y. So whether it's a sum or a difference, you end up adding these and then taking the square root. Well, that's exactly what we're doing here, the standard deviation and the standard deviation. Okay, so that's the shape, the center, and the spread. So the last thing we'll do here, let's go ahead and practice calculating this. Let's do an example. Okay, so your teacher brings 2 bags of colored goldfish crackers to class. Bag 1 has 25% red crackers. So that is our first sample proportion. Sorry, that's just the proportion. That's the true proportion. So bag 1 has 25% red crackers. Bag 2 has 35% red crackers. So that's going to be our second proportion. Bag 1, bag 2. Now each bag contains more than 1,000 crackers. So using a paper cup, your teacher takes a simple random sample of 50 crackers from bag 1 and a separate simple random sample of 40 crackers from bag 2. Okay, now the 50 here, that was from bag 1. That's the sample size for bag 1. And then 40 crackers from bag 2. So that's sample size 2. Let p hat sub 1 minus p hat sub 2 be the difference in the sample proportions of the red crackers. So part A, what is the shape of the sampling distribution of the difference of sample proportions? Y. Well, we're going to test this with the large counts. So if we take the first bag, if we take bag 1, we need to do n times p. So n sub 1, that was 50, times p sub 1. Now they say that the first bag, the proportion is 25%, so that's 0.25. And then 50 times 1 minus 0.25. And if we calculate this out, we get 12.5 here, and we get 37.5 there. Those are both greater than or equal to 10, so that's good. If we take bag 2, now we only took 40, that's our sample size, but in bag 2, 35% of the crackers are red, and then 40 times 1 minus 0.35, and if we work that out, we'll get 14 here, we'll get 26 here. Now all 4 of these numbers are greater than or equal to 10, so that means that our shape is going to be approximately normal. And if we're writing this on a test, we want to write the word approximately. Okay, so there's the shape. Find the mean of the sampling distribution. Well, the mean of p hat 1 minus p hat 2 is equal to p1 minus p2, is equal to the difference of their proportions. So that would be 0.25 was the proportion in bag 1, and then the proportion of bag 2 is 0.35, so the difference will actually be negative 0.10, negative 0.10. So that is the mean of the distribution of sample proportions, of the sampling distribution of sample proportions. And then the last one here, part C, calculate and interpret the standard deviation of the sampling distribution. Okay, so the standard deviation of p hat, of the difference, p hat 1 and p hat 2. Okay, I'm going to write this out here. So it's big square root p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. Now we know the proportion in the first bag is 0.25, and then 1 minus that is 0.75, and we had 50 crackers in that bag, in that sample, plus the second proportion was 0.35, 1 minus that is 0.65, and that had 40 crackers. Okay, and now this is a calculator problem here. So we'll do, whoops, let's take the square root. I'm going to make a fraction, 0.25 times 0.75 divided by 50. And then next to that, plus, make another fraction. All of this is under the square root, 0.35 times 0.65 divided by 40. And we get 0.097, 0.097. Okay, so we calculated it. It also says interpret the standard deviation. Well, what this tells us, this is the spread, okay? Remember that standard deviation is the spread. So we can say the difference in sample proportions typically varies This is not the exact difference for every individual sample proportion. What this is that if we do this many, many, many times, the difference in sample proportions typically varies by 0.097 from the true difference in proportions. And remember, the true difference in the proportions is negative 0.10. Okay, so a lot of stuff there, but not really anything new. All we're doing is we're taking concepts that we learned back in chapter 7 when we're dealing with sampling distribution, except now we have a difference. We have more than one sample proportion that we're looking at. And that is the end of the notes.